Okay, so let me start with, so what have you, maybe I'll start with a little bit of interaction, right? So this is a course on attosecond physics. So how much have you got through, like, do you know what an attosecond is, right? So you know what a short pulse means, right? How do you define a short pulse? For example, what is meant by the amplitude, what's meant by the phase, and so on, right? And also the fact that the phase can be time dependent, right? You have dispersion, you have higher order, something called chirp, right? Higher order derivatives of the phase give you different orders of chirp and so on, and all that is clear. So what I will try to teach in these, maybe I'll split it into 3 to 4 lectures, is trying to lead to the generation of attosecond light pulses. Okay? So the first step in this journey would be to understand what is called harmonic generation. So have you already heard about what harmonic generation is? Right? So what is it? Maybe if you have some 1 or 2 lines on it. So what you do is, so maybe let's draw something. So you take some medium, so you shine some laser pulse on it, okay, and then out comes maybe some other frequency. So you shine something with omega naught, and you get out maybe 2 omega naught, 3 omega naught, and so on. And just, it need not be just 2 omega naught, 3 omega naught, but in general you can generate also frequencies in between. Okay, but if you actually drive it with a very long laser pulse, it turns out that you get integer multiples of the driving laser field. Now what I will try to teach in this particular lecture is the following. What is the source of this radiation, right? How does systems radiate? So if I want these harmonics, there is a medium, right? There is a certain medium, and this medium is what is generating these new harmonics, whether it's second or third harmonics. So what exactly is this connection between light and matter? So we will try to understand this a bit more rigorously with some theoretical perspective, and finally I will show you how the harmonics are generated. Okay, and the reference for this part of the lecture is a classic called Nonlinear Optics by Robert Boyd. I'm sure some of you might have already seen it, but most of the material that I'm going to present here is coming from this book. So let's start with some electromagnetic theory. Okay, so because we just said that, so in order to generate radiation, you need to shine some light on some medium, and then out comes radiation. So if the equations that govern electromagnetic radiation are the Maxwell's equations, so everything is embedded in these set of 4 equations, and I have written it for this particular form where the Maxwell's equations is in matter. So the material system in general can be described into 4 categories. One is the free charges, okay, rho f, the density of free charges. You can have what are called free currents described by some current density vector J, or you can also have a material that can be polarized, which is characterized by some polarization vector, or you can have some magnetization vector depending on the kind of material. So broadly, these are the 4 source terms that enter into Maxwell's equation. So if I have free charges, free currents, polarization, or magnetization. So these are the Maxwell's equations. So the first one is the Gauss law, so divergence of the displacement vector. So the notation here is of the classic book by Griffiths, so I'm sure most of you have seen it. So divergence of the displacement vector gives you the rho, which is this rho f, the density of free charges. Then you have divergence of being 0. Then this is the Faraday's law, curl E is minus derivative of the magnetic field with respect to time, and this is a final Ampere's law with a modification. Now the constitutive equations that link the polarization with electric field is D is equal to epsilon naught E plus P, and H is this magnetization auxiliary vector which connects the magnetic field with the magnetization vector, right. Now in the case of harmonic generation, let's get a little bit specific. Let's say I want to write down the wave equation in vacuum, right. Most of you might have seen this slide. So vacuum is characterized by no free currents, no free charges, no magnetization, and no polarization. Now you can start with these Maxwell's equations, apply with, let's say start with the Faraday law, apply curl on both sides, and you get these derivatives, and you can use this particular vector identity and come up with the wave equation, right. Have you seen this earlier? Yes. So this is so called wave equation, and this governs the propagation of the electric field in vacuum, and the solution to this has usually the form E is some E naught exponential I, let's say it's propagating in z direction, minus omega t with some polarization vector n cap, right. This is the solution to this equation. An equivalent expression can also be derived for the magnetic field. Now what if you have this wave equation but in an inert gas, and you model this inert gas as a homogeneous dielectric, okay. Now what are the sources? So you do not have free charges, you do not have free currents, you do not have a magnetization, but you have a polarization which is homogeneous. So which means it's constant, it has a direction because it's a vector, but it's a constant, it's a homogeneous dielectric. Now if you repeat the same analysis, so you apply curl on both sides of this equation, one of the Maxwell's equations, and what you get is the following. So let's just walk through this. So you apply curl on both sides, right, and on the right hand side you get a second derivative of the displacement vector with respect to time, and you also use this identity curl of E is gradient divergence of E minus del square E. Now since rho is 0, right, the Gauss law gives you divergence of D is 0, right. The Gauss law was divergence D is rho, right. There is no rho, so therefore divergence of D is 0. Now you substitute the explicit expression for D, which is epsilon naught E plus P, right, and now because it's a homogeneous dielectric, there is no derivative, it's a constant, it's a vector, but it's a constant vector, so therefore divergence of P goes to 0, which means you have divergence D is equal to 0, and now you get a wave equation which has del square E is mu naught dou square D by dou t square, okay. Earlier we had mu naught epsilon naught, so let me remind you what we had earlier. In this place we had mu naught epsilon naught del square E by del t square. Now this got modified to, instead of E with a D. Now let's expand this out. So you get two terms, this is the del square E by del t square minus mu naught del square P by del t square. Now on the right hand side you had what was earlier, but you had a 0 on the right hand side. Now you have a second derivative with respect to P. Now if I want new frequencies to be generated in the system, where does it lie? It's really in this polarization that you generate. So the source of radiation is some system which has a time dependent polarization. If I have time dependent polarization, then as the field propagates through this medium, it starts generating new frequencies, okay. Now so in most elementary electrodynamics courses, what you approximate is that this polarization is proportional to E, and you have some proportionality constant which is some epsilon naught times a susceptibility term. Now you substitute this here, instead of del square P by del t square you get a mu naught epsilon naught chi 1 del square E by del t square. Now you bring this onto the left hand side, and what you get is you take this mu naught epsilon naught as common, and you get 1 plus chi 1, and this 1 plus chi 1 you write as the relative permeability, and the square root of that relative permeability gives you the refractive index, and therefore you see that in a linear dielectric medium you have the wave equation, but with the velocity being c by n, okay. Now however, this is not the most general approach. So P being proportional to, so let me go back to this slide, P being proportional to the electric field through a constant epsilon naught chi 1 is essentially an approximation, because why should it just be linearly dependent on the electric field? In general, in general P should be proportional, is a function of electric field, because you take some medium. So let's say I have an atom a very simplistic model of an atom. There is a positive charge cloud that's well confined, that's your proton, let's say this is a hydrogen atom, and there is an electron density for the electron, right? This is more smeared out, this is for the proton. Now if you put in a field, let's say I put in an electric field, then the electron gets pulled out in one direction and the proton gets pulled in the other direction. But then there is a mass effect, proton doesn't move much because it's much heavier than the electron, and electron moves a little bit more. So what would happen is the proton, let's say, approximately remains there, but the electron cloud would spread over like this, right? Now the stronger is a field, the more it gets pulled over. That's what our physical intuition should say. So therefore in general the polarization should be a function of the electric field, but a more general expression for this polarization should be, if I expand it in a Taylor series, right, for a small field about some mean value of the electric field, then I get an expansion which looks like P is equal to C1e plus C2e square plus C3e cube and so on. So that's the most general expression for the polarization vector. Now instead of just taking the first term in this, that's the linear term, that's the epsilon naught chi 1 e, if you also take the second term, let's say the epsilon naught chi 2 e square, now you do the same analysis, right? You get this term will give you exactly the same terms as earlier. The earlier term was the following: the speed of the light was reduced by the refractive index, but you get an extra term which is mu naught epsilon naught chi 2 and a second derivative of e square with respect to time. That comes from this term, right? Polarization had two terms. The first term gives you what we had seen in the earlier slide, and the second term will give you the derivative with respect to e square. Now if e is e naught exponential I kz minus omega t, now you square it, you see that it gets e naught exponential I 2 kz and 2 omega t. You see that now the solution has an additional term which is oscillating not at omega frequency but at 2 omega frequency, right? Now this is a source of a second harmonic. So basically polarization not being just proportional to the electric field, but also polarization being proportional to e square. Now if I have e cube term, then that would generate a 3 omega term. If I have, so e square generated a 2 omega term, e cube would generate a 3 omega and so on, right? So this is how the second harmonic, third harmonic enters into this wave equation, and as the field propagates through the medium, it starts collecting field which is not oscillating at omega but at 2 omega, 3 omega and so on. Okay, maybe I will pause here. You have any questions?
You mentioned about this expression, the way the polarization is sort of expanded in terms of the Taylor series, it's only for small fields.
Yes, for small fields.
But usually Taylor series is more like a general expression, right?
So when I say small fields, okay, maybe I should make it more accurate. So such an expansion is meaningful for small fields because you can truncate it after a few terms. But if you have a large field, it means that you basically need to take all terms for it to have a meaningful value. Okay. So for small fields, it makes sense because you can truncate it after the first, second or third, depending on the field strength. I meant in terms of the usefulness of the expression.
So you also previously told that you can also get frequency between 2 omega and 3 omega. Then how do you get this field?
I will show you later at the end. Yeah, I'll show you later. See, basically you need to think about it in terms of Fourier transform. So if I just have a very short pulse, then its Fourier transform does not have very clear contribution from these integer multiples of the frequencies. You see that it's basically a broad, something which has a lot of frequencies with a certain bandwidth, which will be related to the temporal duration. So you cannot say I have exactly these, but I have a distribution of frequencies within that window. But if I have a many cycle pulse, essentially something like a monochromatic or an infinite cycle pulse, then I can start seeing exactly those peaks that are harmonics. But you will see something towards the end of not today's lecture, but later. Yes. Anything else? So, to keep it in a nutshell, what I've shown you is you start from the Maxwell's equations. Radiation comes from either time varying currents, time varying charges, time varying polarization or magnetization. The case of importance for attosecond physics in terms of the typical sources that we have is that of an inert gas, which can be modeled as a homogeneous dielectric, and there the source of generation is a time dependent polarization. So we have neglected all the other terms, plugged in a time varying polarization, and then we showed how on expanding this polarization as a function of the field, how new frequencies enter into the Maxwell's wave equation. Okay, so that's for the first part. Okay. Now let's get a little bit more deeper into the microscopic origin. Okay, we just said I can write down a Taylor series in terms for the polarization, but let's get a little bit more deeper. I want to know what is exactly happening in the atom, right? So now I need to really describe the atom and see how does it respond to a certain field. So for that we need to just a few quick pointers. I'm assuming that most of you have done a quantum mechanics course. So if I take any atom, the state of the system is described by a wave function psi, right? And the evolution of this psi is given by the time dependent Schrodinger equation. Okay, that's the time dependent Schrodinger equation, and the evolution is governed by whatever is a Hamiltonian. Now a polarization, if I assume approximate the system to be a dipole, so as we said, there is a positive charge center and there is a negative cloud, and the mean of this negative cloud is shifted. So let's say this is the shifted mean of this electron cloud. I am generating a dipole, right? So now quantum mechanically, what is meant by a dipole? It's essentially q times expectation value of r. So classically I would write it as q times r, which is the distance between the two centers, the positive and the negative charge centers. But quantum mechanically I cannot define a position as a, I cannot compute position, but I can compute the expectation value of the position. So therefore the polarization is charge times r. But now in a real system I don't have a single atom, but I have a collection of atoms. So therefore I need to multiply by the charge, or sorry, not the charge, the number density, or just if I have 10 particles I will multiply this response by 10. If I have 100 particles I multiply by 100, right? If I take a gas and it has 1,000,000 particles, then I would multiply it by 1,000,000, right, in the simplistic way. Now a more general way would be to exactly consider the gas density profile or the intensity profile of the incident beam and do various kinds of averaging. So you just generalize the way you sum it over, right? But underlying is this p atomic. So I should be able to compute this p atomic, right? And then from this I should be able to analyze what are the harmonics being generated. So it's hidden in this time dependent dipole, which can be computed as q expectation value of r, which changes with time. Okay.
Yes. Should there be some constraints on the density or packing fraction for you to assume that it is a homogeneous medium, the gas, since they're individual atoms? Should there be some configurational constraints for it to be a medium?
So no, you have gas, it's basically randomly oriented. So, and also if you look at typical densities, right, and you look at the fields, so it's the wavelength is pretty large compared to maybe the spacings, right, or comparable, and then you can basically assume a kind of an averaged effect. Of course, as I just said, in a more detailed analysis you need to take into account all of that, but for the simplistic analysis you can just multiply by the number of atoms. Okay. Anything else on the previous slide? Yes, please.
You said that P total is n times P atomic, right?
So that's a very simplistic approximation. So if I have all n atoms seeing the same thing, then I would multiply it by n. That's a very simplistic approximation for the purpose of the lecture. But for a research purpose, then that's not sufficient. Okay? You need to make sure that that all the atoms are basically seeing the same field as the beam is propagating and so on. So that's why that's more details which we don't have to cover here.